So, just as a quick review, the reason why we even have to do this kind of thing is because in the real world, in forensic testing laboratories, blood testing laboratories, urine testing laboratories, like LabQuest and no, sorry, LabCorp and Quest Diagnostics, they are all, in addition to forensic science labs, they are all accredited by an organization called ANAB, or they like to be called ANAB. It stands for the ANSI ASQ National Accreditation Board. They don't like to be called ANAB. They either be like to be called by their their acronym or their actual name. So, and all testing laboratories, all chemical testing laboratories, are are accredited at a standard with a standard called the ISO 17025 standard, right? And in that standard, it says this: all quantitative measurements, right, must have uncertainties applied to them. And so, when you're an analytical chemist, that means that anything you measure is a quantitative, you know, value, and therefore you've got to measure it. You've got to apply a uncertainty measurement on it. Um, and the reason why this is because and we've discussed this before, but just as a little recall and a little reminder, whenever we measure something, it's just an estimate, and we want to be as close to the true value as possible. And we have to tell people when we report our data how far we are, or what are the limits of what our data is, and compared to the true value, right? And so we do that with doing the uncertainty budgets like you're going through right now in lab, and then also we do that by doing propagation of uncertainty, and then also we use statistical tests to figure out whether or not our numbers are reliable or not, right? And so, um, just as again as a quick review, why do we even have uncertainty? I thought that my graduate cylinder was pretty certain. I thought that my beaker was pretty certain. Well, actually, you probably didn't think your beaker was very certain because you were told ever since Gen Chem that the least accurate way to measure volumes was with a beaker, and the most accurate volume way that you had at your disposal at the time was a volumetric flask. But if you take a close look at these different glasswares, there's a graduated cylinder right there. There's a volumetric flask right there, and then here's a beaker right here. You can see that all three of them have a plus or minus on it. So they're before these pieces of glassware have been shipped to us at the manufacturer, they've already gone through to see what the different uncertainties are on the glassware, right? But that's just on the glassware itself. The reason why you have to go through and do all the stuff that you're doing in lab right now for the uncertainty budget is because you have to also take into account the other measuring devices you're using in an experiment, like the balance or the pipetters, and also you have to take into account the human error, right? And so, or I guess in the parlance of the ANAB, they like to call it operator error. Anyway, when you look at these different pieces of glassware, right, you can see that there's a 5% plus or minus 5%, uncertainty on the beaker. Wow, that's a big uncertainty on the beaker, right? So what that means is that if you had a 100 ml beaker, right, 5 mils, it could be, and you filled it up to 100 mils, it could be actually 105 mils or 95 mils, right? Uh, and so when we see an uncertainty that's plus or minus a percentage, that's called a relative uncertainty. And if you have a relative uncertainty on a piece of glassware, that means it's not a very accurate piece of glassware. Like, you could not depend on those measurements. They're going to be all over the place. And as you can see here, on this 250 ml beaker, you have a 5% uncertainty, plus or minus. And the other thing about it too is that on relative uncertainties, the larger the volume, the more inaccurate it is, right? The more uncertainty it is. So this is a 250 ml beaker, so off the top of my head, I don't know what 5% of 250 is. So let's see here, 0.05 times 250, that's 12. That's 12.5. So if you use this beaker and you try to measure out 250 mils of water, you could be off by 12.5 mils plus or minus, right? So you could actually be measuring out 262.5 mils or 200 and whatever 250 minus 12.5 is. I'm not going to do that right now. Anyway, so obviously the least accurate way of measuring volumes is with a beaker. We can move up to the next one. The next one that's a little bit better than a beaker is a graduated cylinder. And the graduated cylinder says that the uncertainty is plus or minus 2 mils for a 250 mil graduated cylinder, which is great, right? Because, well, not great, but at least it's not a relative uncertainty. This would be called an absolute uncertainty. And in an absolute uncertainty, it doesn't change, right, with the more the volume like it does with the relative uncertainty. So that's a good thing. But the number two is that, you know exactly how much uncertainty you have there, because if you were to measure out 250 mils, right, it's a plus or minus 2 mil uncertainty. That means that it's either going to be 252 mils at most or 248 mils at least, right? At the very least, if you try to measure out 250 mils on a graduate cylinder. Now compare that to the 12.5 mil difference plus or minus on a beaker. So there you can see what is the more reliable way of measuring volumes. It's going to be a graduate cylinder at the moment, right? So we move on to the very last piece of glassware, the one that was told to you in Gen Chem that was the most accurate way that you had available to you to measure some volume, the volumetric flask, right? Remember, a volumetric flask doesn't have graduations on it. It's got a little laser etching at the very top. And that laser etching, as long as you have the meniscus of the liquid on the bottom of the meniscus of the liquid on the laser etching, you should be getting a pretty accurate volume. And so this is borne out by the fact that if you look at its uncertainty here on the side of the graduated cylinder, on the side of the volumetric flask, that the uncertainty is plus or minus, plus or minus 0.15, right? Plus or minus 0.15. That's only 150 microliters. So for a 250 milliliter volumetric flask, and you try to measure out 250 mils on it, which that's the only thing you can do on it, it's only going to be off at most or at least by 0.15 milliliters or 150 microliters, right? And so you can see how a volumetric flask is more accurate to use to measure out volumes, because these of the uncertainty associated with it, which is 0.15 mils or 150 microliters, as compared to the graduate cylinder, which is at 2 mils, right? Not as, less accurate, but not as bad as the beaker, which is 12.5 at 250 mils, right? So as you go through your labs this semester, you're going to be using these glassware, right, to measure out volumes. And so you're going to have to be able to propagate the uncertainty of those volumes using with the glassware you used, right, in your calculations. And that's what I'm going to show you how to do today. The other thing about it too is that you have to be able to decide, right? Because remember, I told you at the very beginning of this class that the point of this class is to make you a good scientist, right? And so you're going to leave this class knowing how to be a scientist. And therefore, one of the things that a good scientist does is they problem solve. And so you need to be able to decide which glassware or any equipment for that matter is appropriate for the job that you want to do, right? So if you're, for example, just making a buffer, right, that where volume really isn't that important, right, then you can use a graduated cylinder. Whereas if you're trying to actually make a standard solution, right, with from a stock solution using dilution, right, you have to be able to be accurate about that, and therefore you would be using a volumetric flask there, right? And the only reason why you would be using a beaker is just to transfer large volumes of liquid around, right? Just so that you could have something to pipette out of or something, right? But you would never be using a beaker as a sole measurement device, okay? All right, so let's go ahead and do the very first example here. In this example, you'll be measuring out 11.6324 grams of sodium rhodesnate on a balance that has an uncertainty associated with it of plus or minus zero point 0.3 milligrams. Okay, so a couple of different things to note before we move on with this question. Sodium rhodisnate is a compound that we use in the crime lab to detect gunshot residue. Specifically, it detects lead. And then also, you might be asking yourself, where did we get the uncertainty that's associated with this balance being 0.3 milligrams plus or minus? Well, you're actually carrying out that procedure right now in lab, where you are doing the uncertainty, you're developing and calculating the uncertainty budget for the balances that you'll be using for the rest of the semester. And so when you come up with the uncertainty from those balances, weighing out the 25 times for each of the standard weights, right, you'll come up with an uncertainty value, and that value is what you'll be using for the rest of the entire semester for whatever balance you're using, right? And so this number here comes from the fact that someone else went through for this particular question, quote unquote. An uncertainty budget was made for the balance that was used here in this example question, and that budget turned out resulted in an uncertainty of 0.3 milligrams plus or minus, right? And so a lot of work goes into getting an uncertainty value for different instruments, and it's not as easy as just looking into the instruction manual and seeing what its uncertainty is, because the instruction manual of a balance only really provides you with the linearity of the instrument, the balance, and the readability of the instrument. It's up to you to actually create the uncertainty budget that you'll use to calculate the uncertainty of the associated with the balance that you'll use in your uncertainty calculations for the rest of the semester, right? So that's an important number there. So this 11.6324 grams of sodium rhodisnate was dissolved into 250 mils, right, in a 250 mil volumetric flask, or that containing water. This volumetric flask had a uncertainty associated with it of plus or minus 0.15, right? And so this kind of calculation that you're going to be doing here in this example is going to be a very common calculation that you'll be doing in lab, right? Where you're you're calculating the concentrations of solutions, either by doing a dilution calculation like M1V1 equals M2V2, or just determining a concentration by dissolving a solid into some water. And so both the volumetric flask that you're using and the balance that you'll use so both the volumetric flask you're using to hold the water and the balance you're using to weigh out the solid are going to have uncertainty associated with it. And so when you report concentrations for every single lab that you do for the rest of the semester, it needs to have uncertainty associated with it. And this is how you will calculate it. So just like the question says, determine the concentration in milligrams per mil, right? And then also report its corresponding uncertainty. So how do we do that? Well, the first thing we have to do is to use the values that are given to us, which are the 11.6324 grams of sodium rhodisnate and the 250 mils of water to determine what the concentration is in milligrams per mil. So how do you do that? Well, that's easy. Milligrams per mil is literally a mass of milligrams divided by a volume of milliliters, right? And so you measured out here 6324 grams, right? But I didn't ask for the concentration in grams per mil. I asked it for milligrams per mil. So before you can even carry out this division right here, this division calculation right here, right, you have to convert the grams to milligrams, which is actually really easy because milligrams is only 3 decimal points away from grams. So all you really have to do is move the decimal point from here over 3 spots, right? And once you move it over 3 spots, then you get 11,632.4 milligrams. And then you can divide that by the 250 mils given by the problem, and then you'll get a concentration of 46.5296 milligrams per mil. But you're not finished yet, right? For 2 reasons. Number one, you still have to give a corresponding uncertainty, right? You have to give a corresponding uncertainty. And then also, we don't ever report concentrations with that many decimal points, right? And in Gen Chem, you're always told to use the measurement that had the smallest number of significant figures as your guide for how many significant figures to have in your final calculation. Well, now at this point in your chemistry careers, we're going to put a pin on that, and we'll come back to actually reporting this number the correct way in just a second after we carry out our uncertainty calculation. Okay, after we carry out our uncertainty calculation, and so the next step then is to choose which equation to use, right, to do our propagation of uncertainty. So this first equation here, where we have y equals a plus b minus c, right, what that means is the y here is the value of concentration you got from a mathematical operation, right? Same here. This y is also that as well. And so the rest of this equation is asking what mathematical operation you had to carry out to get to that y, right? Well, to get to this y, which is the 46.5296 milligrams per mil, you actually have to carry out a division operation, right? This is a divide or division. If I know how to spell division. There we go. Division, okay? Well, for this equation over here, this equation only applies to if you had to do a addition operation or subtraction operation. So that's not the equation you'll be using for this particular example, right? I'll give you an example after this one where you will use that equation, but for this one, you're not going to use that one, right? You're going to use this one over here, right? Because for this one over here, if y is the result of a multiplication or a division operation, this will be the equation that you use for the propagation of uncertainty. Okay, and so of course I boxed it there to show you. And so how do we use this equation? Okay, so this equation is actually quite easy to use. Not as easy as the first one, but it's pretty easy to use. The thing to note though is that when we have Sy over y, this is actually known as the relative uncertainty. This is known as the relative uncertainty. I don't know what's happening here, but I'm trying to write and it keeps on getting in the way. Okay. It doesn't let me writing there, so I'm going to move this over there. Relative. There we go. That's the relative uncertainty when you have the y over y, right? And so this y here, again, is the value you got from doing the concentration calculation. And then this Sy right here, right, that's going to be your absolute uncertainty. And as you saw in the previous, slides, we were looking at the graduated cylinder and the beaker and the volumetric flask. It's actually best to have the absolute uncertainty. So our calculation will always have a goal of getting the absolute uncertainty. Okay. And so, of course, again, just so we don't forget this, so the y is actually the concentration that we calculated. Okay. So this equation is easy as pie to use. The SA here in this equation, the SB here in this equation, and the SC here in this equation are the uncertainties, right, that are associated with each one of the measurements. So for SA, the uncertainty that was associated with it would be the 0.3 milligrams. Okay, and so that's why the 0.3 milligrams go in the first place, right, in the first spot, right there. And then the A here, right, is the measurement from that first uncertainty, right? And so the measurement from that first uncertainty was the 11.6324 grams, or converted to the milligrams per mil, and then it actually became 11,632.4, right? And so that's what goes down here in the bottom equation, right? The bottom of the denominator. Okay, and then for SB, that's the uncertainty that was associated with the volume measurement. So that's the 0.15. Okay, so there's the 0.15 right there. And then the B itself is the volume that was associated with that, which is the 250. which is what we see here, right? And so you do have SC and over C, but we don't have any other calculations to add onto that, right? But if you had more calculations or more measurements rather to add on, you can go infinitely for with the terms in this one, right? So once you plug that in, it's going to be once you plug these values into the equation, it will be you can get the relative uncertainty by doing the square root, right, of the sum of the square of the uncertainties divided by the volume, the measurements, right? So we square the 0.3 divided by 11,632.4, and then we square the 0.15 divided by 250, right? And we get these values here, right? Oh, sorry, I just did the division there, right? So now what we'll do is we'll square them, right? And that's after we square them, we'll take the square root. And when we take the square root, we get this very long number here, okay? So that's a very long number. But again, this number is actually only the SY over Y, right? The relative uncertainty. We want to have the absolute uncertainty. And so how do we solve for the absolute uncertainty? It's actually really easy because where do you know what Y is? Y was that concentration, right? From before that we calculated. So all we have to do then is plug in the Y. And so as you can see here, we plug in the concentration from before into the Y, and now we can solve for SY, which is the absolute uncertainty, right? And so when we solve for SY here, the absolute uncertainty here, right? And this is as easy as multiplying both sides by 46.5296 from the original concentration that we calculated. We get the SY, or the absolute uncertainty right here. Just to be clear, SY is absolute uncertainty. Okay, to be 0.0279437, right? And again, that's a very long number, and honestly, generally we don't really even like report uncertainties more than 2 digits, right? But the more formal way of doing this is deciding by significant figures. And again, if you look at the original problem, okay, if you look at the original problem, the lowest number of significant figures in any measurement up there in the original problem is the 250 mils, which has 2 significant figures, right? And so what that means is then we will go ahead and round it to 2 significant figures, right? And that gives us a uncertainty of 0.03, okay? And then we will also do the same to the concentration here and get that to 2 significant figures, right? Or 2 decimal points is what I meant to say, right? And when we get that to 2 decimal points, we'll round it up because that last digit there was a 9. And so now we report our answer here as being 46.5 milligrams per mil plus or minus 0.03. Now let's do an example in which the uncertainty propagation involves a mathematical operation of addition or subtraction, right? So let's just remind ourselves that when Y, some calculated value, right, that you've gotten, is A plus B or minus C, right, where the operation to get that calculated value is addition or subtraction, SY, or the absolute uncertainty involved in that calculation, equals the square root of the uncertainty of A squared plus the uncertainty of B squared plus the uncertainty of C squared, right? And of course, you know, it doesn't just end with C. You can go as long as you need to go to satisfy your uncertainty propagation calculation, okay? So the most common place that you'll be using this kind of equation will be doing a titration, right? And why is it that in a titration you'll be doing this so often? Well, that's because you're going to be reading a burette, right? Because in a titration you're always reading a burette, okay? So why does that mean then you'll be using this type of equation then? Well, think about it. Here I have my burette, okay, and here's my stopcock. Here's my burette. Here's my flask. Right, there's my flask. And generally you'll put a base and an acid-base titration, B for base, B for burette, into the burette. All right, and then you'll drop liquid into base into a volume of unknown acid, right, to determine its concentration. Well, how do you read a burette? Well, you read the burette by looking at the initial volume, right? And then looking at the final volume once you've reached the endpoint of the equivalence point of the titration, right? And then to determine the concentration of the unknown acid, you have to figure out what the total volume of liquid or base was dispensed into the flask. Well, how do you figure that out? Well, the equation is Vt for total volume equals the final volume minus the initial volume, right? Excuse me. And so, as you can see in this calculation here, you're doing a subtraction operation, right? Which is consistent with this subtraction operation up here for an uncertainty of measurement propagation or error propagation, right? And so that's why you would be using this equation, okay? So let's do an example then, okay? Say then your initial volume was 0.24 mils plus or minus 0.05, okay, on this burette. And again, just to remind you, right, you will go through in lab the propagation, sorry, not the propagation, but the uncertainty of measurement budget, all right, procedure for developing an uncertainty for burettes. And so your number is not going to be this 0.05 in this particular example here. Your number will be whatever it is after you've gone through and you measured out certain volumes, right, predetermined volumes from a burette and weighed them, right, to determine your own uncertainty for the burette. Okay? And so let's say the final volume then is, sorry, not 0, but 12.52 mils plus or minus 0.5, right? 0.5. Sorry, 0.05. Okay? And it's the same uncertainty because you're still using the same burette for both volumes right there, right? So it's the same uncertainty for both. And so I forgot to talk about this in the last example, but a common question is why don't we just add up, the uncertainties, and then we can, we don't have to go through any kind of special equation. Just add up the 0.05 plus 0.05. Wouldn't that give us a good enough propagation of uncertainty or propagation of error? Well, that's true. You could do that, but the thing about it is that if you did do that type of calculation for the propagation of error, your calculation would be, your error or your uncertainty would be abnormally large, right? And so abnormally large meaning that it assumes that that every one of your measurements is off by that much, okay? And it's very unlikely that all your measurements are off that much, right? I mean, you're in this class, you're in analytical chemistry, you should know how to read a burette, and so none of your measurements should be off by that much all the time, okay? And so that's why we use the propagation of uncertainty or propagation of errors equations to do this kind of calculation, and we don't just straight up add up the uncertainties, because then we just have an overwhelmingly large uncertainty that would not be useful anymore. Kind of like when we had the example with the chocolate bar and the caffeine. Remember the guy in class? The guy found out the concentration of the chocolate bar was 10 milligrams, but then the uncertainty was plus or minus 7 milligrams. I mean, that's more than half the actual mass, or half the actual mass that was available in that chocolate bar, right? I mean, and so when you have an uncertainty that large, the value is no longer even reliable, right? It's worthless. And so, and don't forget that your grade in this class, especially in the lab, is dependent upon the fact that you are within 5% of the true value, right, or the actual value in all of our experiments when you're trying to determine the concentration of something or how much something is there. And so if you have an uncertainty for a balance or for a pipetter or for a burette that's abnormally large, your uncertainty might exceed the 5% that's required for you to have an A, right? And we wouldn't want that. And that's the reason why we have to go through doing these kinds of propagation of error or a propagation of uncertainty kind of equations instead of just adding things up as if they were a completely additive effect, right? So, given that we have this example here where we started at 0.24 mils plus or minus 0.05, funny thing there is I guess we tried very hard to get to 0 here at the top of the burette, but we weren't quite close enough to 0, right? The meniscus was just below the 0 line. And so that's why it's 0.24, right? And then we ended with the volume being at 12.52, right? And so to find our total volume, VT, equals the final, which is 12.52, minus 0.24, which then equals, if we just do that very simple math, 12.28, right, mils. Okay, 12.28 mils. But we're not done yet, right? Even though we've gotten the final volume already, we haven't done our propagation of errors yet, right? And so this is where we will go in and use our propagation of errors equation, right? Where SY, which is the absolute uncertainty, is equal to the uncertainty of the first measurement, right? And so that's 0.05. Sorry, I lost my train of thought for a second here. 0.05 squared plus the uncertainty of the second measurement squared, right? The square root of the uncertainty of the first measurement squared plus the uncertainty of the second measurement squared. Okay, it's that simple. Okay, plug that all into the equation, and the number you should get is a very long number, as always. 0.070710678. Okay, very long number. So very much like the equation or the previous example where we did multiplication. Not multiplication, dividing to get a concentration. In this one here, we will also move it so that it gets to 2 decimal points, right? Basically to match up with the uncertainty that is that's associated with the burette, right? 2 decimal points. And so we'll take all the rest of this off. We have a 0 here. That's good because then we don't have to round anything, right? And so now then our certainty is 0.07. And so we'll report this as 12.28 milliliters plus or minus 0.07. And that's how we would report that, right? And if you want it to be really complete, you can always put on the end the volume again, or the unit again, mils. Okay? So you'll be doing a lot of titrations in the class, or in the lab rather, and whenever you do the titrations in the lab, I expect that all the volumes that you calculate from the final minus initial on those burettes to have an uncertainty of measurement, uncertainty of propagation of uncertainty applied to each one of those measurements, right? And then you also have to, for the concentrations, use the other propagation of uncertainty equation too that involves division or multiplication. Okay, so all of your numbers that you calculate and you measure should have some kind of error or uncertainty associated with it. Okay, I keep on saying error, but I apologize. I mean to say uncertainty. Error is a single number, right? Whereas uncertainty is a plus or minus value. So you should be having an uncertainty applied to all your measurements and all your calculations. And again, you'll get those uncertainties to plug into the uncertainty equations, propagation of uncertainty equations, from the uncertainty budgets that you are creating right now in lab. Okay? So now let's talk about some statistics that you'll be using in analytical chemistry lab. Okay? So, statistics for analytical chemistry lab. Okay. Well, the first term is a pretty easy one that we all should be very familiar with is the mean, right? And there are definitely differences in the definition between mean and average, right? But for the purposes of this lab, in this class, all I need you to know is that x bar, which is the mean, equals the sum of all the observations. And I messed that up there because I forgot to put the little I under the sum sign. So let's write that again. The sum of all the observations divided by the number of observations. Okay? Divided by the number of observations. Don't forget to dot your I's. Okay? And so the I just represents each observation, whereas the N is the total number of observations. Or measurements. Okay? The other term that we're going to be using a lot is the standard deviation. And the standard deviation is S, is its symbol, equals the square root, right, of the sum of each of the observations minus the mean, all divided by n minus 1, right? All that is under the square root symbol, okay? And just in case you were not aware, n minus 1 here is known as the degrees of freedom. Right, so if anybody ever asked you, or if any questions ever asked you, what the number of degrees of freedom is, right, or if the degrees of freedom is required for a particular calculation, it's always going to be n minus 1, the number of observations minus 1. And that's the degrees of freedom. Okay? So one of the very first questions that you'll ask, right, when you get done with a data set, especially when you compare your data set with your lab partner's data set, is this question here. I spelled that wrong. Are two data sets statistically different? Okay, that's a question you'll ask yourself, right? Or you not ask yourself, but a question that you need to ask yourself, right? When you're looking at your data and your lab partner's data, right? Because it's something that I want you to report on your lab report. Okay? Another way of saying statistically different is saying are the differences statistically significant? I'll use both of those phrases interchangeably. Okay. All right. So you can actually approach this question two ways, right? The first way is by comparing the standard deviations from both your data set and your lab partner's data set, right? So first we're compare the standard deviations. How do we do that? How do we compare the standard deviations of the two data sets? Well, it's quite easy. We have this thing called the F-test. And in the F-test, F calculated equals the square of the standard deviation of the first data set divided by the square of the standard deviation of the second data set, right? And if you didn't know, when you square standard deviation, this is called the variance. Oops, sorry about that. The variance. Didn't mean to skip a slide there. Oh, and I think I skipped a letter there. Variance. Missed the C in there. There we go. The variance. Okay. And so once you have the F calc, if the F calc is greater than the F that is found in a table of critical F values, then the standard deviations are indeed statistically different. Okay, they're statistically different. So let's take a look at a table of F values real quick. Okay, so we'll go ahead and exit out of PowerPoint. And if we go into there, right, into our Blackboard, and then into the lab modules, and this time we're going to go into important lab documents, right, because you'll be using these statistical tests for almost everything that you do for the whole semester, okay? And so here under statistical resources, you'll see the critical values of F. And other critical values of F, you have to look up the degrees of freedom. Look up your value by degrees of freedom. So if you were actually doing this experiment, or sorry, doing this test with the data sets from both you and your lab partner, each data set was supposed to have 25 data points, right? And so that's the n, right? And so the degrees of freedom would be 24, right? Because it's n minus 1 is the degrees of freedom, right? And so if you take a look up here, right, on the table, get a really close look here, right? You see that these are the critical values for F at an alpha, right, also known as a significance level, right, of 0.05, right? That actually corresponds to a confidence level of 95%, right? And you'll see that throughout all of our statistical analysis and everything we do in uncertainty, we will always be using a 95% confidence level, which corresponds to a coverage factor of 2, which also corresponds to a distance from the mean of no more than 2 standard deviations. Okay, so that's important to remember. We're always going to be using a significance level of 0.05 or a confidence level of 95%, right? They both mean the same thing, okay? And so here's the degrees of freedom for the very first data set, and here's the degrees of freedom for the very second data set, right? So degrees of freedom here would be 24, since you had 25 data points for each one of the measurements, right? And so let's see if we can find 24 here. I need to scroll a little bit here so I can see the whole table. And we can move over. There's 24 right there. And we'll scroll down here to 24. So there's another 24 right there. So we look at that right there. 24 for the first data set, and then 24 for the degrees of freedom for the second data set. And our critical F value is 1.983, right? So what does that mean then? If you were to take the ratio, right, of the square of the standard deviation from the first data set to the square of the standard deviation of the second data set, right? Or basically meaning divide. You take the standard deviation squared of the first data set, divide that by the standard deviation squared of the second data set, and the number you get is larger than 1.983. That means that your values are significantly different, right? Or statistically different, right? And so that's one way to determine whether or not your data sets, namely you and your partner, right, are separate, are different, okay, or are statistically different, okay. The other way to do this calculation to determine whether or not your data sets are significantly different, sorry, I keep on saying significantly different. It's statistically different, or the differences are statistically significant, okay. And so the other way to do it is by using the t-test, right? And so let's go back to the PowerPoint and we'll do the t-test now. Let me get back into that, and then get this going over here like that, and there we go. Okay. And so two you're going to compare the means. And the way you compare the means is by using the t-test. Okay? The t-test. And so the equation for the t-test is this. It's a little bit more complicated, but that's okay. You can handle it. T, calculated, equals the absolute value of the mean of the first data set minus the absolute value of the mean of the second data set, all divided by this value that we called, or a term we called S pooled, which we'll get back to in a second. S pooled is the standard deviation pooled. We'll get back to that in a second. All that is multiplied by the square root, right, of the number of observations from the first data set times the number of observations from the second data set, divided by the number of observations from the first data set plus the number of observations from the second data set. Right? And then the next question is then, how do we get S pooled? Well, S pooled has an equation, and its equation is this. S pooled equals the square root of all the stuff here, which is the standard deviation of the first data set squared, multiplied by the degrees of freedom of the first data set, all that, plus the standard deviation squared of the second data set, multiplied by its degrees of freedom, right? And then all that is divided by the number of observations in the first data set plus the number of observations in the second data set minus 2. Right? And so all these values are actually available to you, okay? You should have the mean for the first data set. I mean, that's provided to you by Excel. You should have the mean for the second data set, also provided to you by Excel. You should have the number of observations for both the first and second data set, which is 25, right? And then you should also have the standard deviation for the first data set, the standard deviation for the second data set. You should have the degrees of freedom for the first data set and the second data set. Both of those are 24. Okay? And then the number of observations again, minus 2. So though the equations look kind of complicated, they're not that complicated. You have the values, you just need to plug them in. Okay? So after all that is said and done, and you get the t-calc, if t-calc is greater than t-table, t-value found in the table, right, in the table of t-values, right, then your data sets are statistically different. Statistically, man, spelling is a problem for me today. Statistically different. Right? Statistically different. So let's take a look at the t-table real quick. And escape. Keep. And if I look at my Blackboard again, and I go back to my statistical resources and look at my t-table, right? My t-table here also looks up things based on degrees of freedom, right? So we want a degrees of freedom of 24, right here, right? Both of them are 24, so we can use 24. And again, so we're going to be using, there's two things here, right? There's the one-tail t-test, and there's a two-tail t-test, right? Well, all of our measurements are based on a Gaussian or normal distribution. So what that means then is that you'll be using a two-tailed t-test. And in my next video, which is the one where we're developing our uncertainty budget for the balance and for the pipetters and all that, we go into detail about Gaussian/normal distributions and what it means to have a two-tail, right? But just for the purposes of this example, just know that we're going to be doing two tails, right? The two-tail test, t-test. And then also, recall that I said that we're going to be using an alpha, right, or a significance level of 0.05, right, which is right there, 0.05%. Or if you don't want to do that, if you scroll down to the bottom, you have a confidence level at the bottom too, right here. And here's 95%. So notice confidence level of 95%, right, is the same column as the significance level being at 5%, right? So they're like opposites of each other. You can use either one to figure out what you need. And so we'll find 24, which is right here, okay? And I didn't realize that it was that small on the screen, so I'll zoom in. There we go. It's a little bit better. Right, and then I'll move over here a little bit. And there's 24 right there, right? And then if I go all the way across 24, there it is right there, 95%, 2.064. So if my t-calc is bigger than that number, 2.064, then my two data sets are statistically different. All right. Excuse me. So that takes us to our very last test, right? And our last test is what we use to determine whether or not an outlier can be removed as an outlier. How to deal with an outlier, basically, right? And so let's do that real quick. We gotta get everything set up to right. There we go. Okay, so the next question to ask then, right, is how to deal with outliers, right? And commonly, right, most people will look at a data set and they can see some of the numbers on the data set and they look a little bit different, or maybe a lot different than the rest of the data sets. They're abnormally high or abnormally low, and on the face of it, they look like an outlier. But technically, you can't actually get rid of those outliers just willy-nilly because they are numbers that you were measured during the course of an experiment, right? So for you to be able to remove those outliers, these outliers, by the way, skew your results to be very far from the true value, which is a problem, right? So to be able to remove those data points that are that can be possible outliers, you have to do a statistical test, right? And there's several statistical tests that you can do to do this, right? But the one that we'll do here in this class, right, will be the Grubb's test. And it's probably the easiest outlier removal test there is, right? But the good news about it is that if you do this and it proves that or demonstrates that your supposed or your questionable data point is an outlier, then you can remove that data point and guilt-free, right? And so the Grubb's test is simply this, right? G equals the absolute value of the questionable data point there's got to be an easier way to abbreviate this, but I'm just going to write it all out, right? The absolute value of the questionable data point minus the mean, right? All divided by the standard deviation. Okay? It's that simple. Thus, if the G calculated, right, and this is G calculated, by the way, is greater than the G found in a list of critical G values in the TG table, right, then the data point is indeed an outlier, right, and you need to reject it. You need to reject it, okay? So let's do one last thing in this video here and look at a table of G values. Again, we can go back into our Blackboard, scroll up to the statistical resources, and then here we have our critical values for G. For critical values of G, it doesn't ask for degrees of freedom, it actually asks for a number of observations, which is N, which is nice. And so we'll zoom in here. Okay, and you see how it asks for the number of observations being N right there, right? And again, right, which of these do we pick, right? And we pick the one that corresponds to a 95% confidence level, which for us would be the 5% significance level, which is this one right here, right? The second to last one in this table, okay? So we know it's the second to last one on the table. And so we'll go down to 25, which is the number of observations we have, all right? And here it is, the G value that we want. Sorry, it's a little low, let me roll up. The G value we want to compare to is the 2.663, right? Because that's where the upper limit or the upper significance level is 5%, and then we are at an n equals 25, right? Number of observations equals 25. And so if we do our G calculated, right, and the number is bigger than 2.663, that means we can remove it because it's been statistically demonstrated to be an outlier, and we can remove it so that it doesn't skew our results. And that actually ends this particular video. Look out for the next video where we talk about how to develop an uncertainty budget and validate instruments like balances and pipetters. If you have any questions, let me know, and I'll see you in class.